Welcome to another devlog for my still unnamed dungeon crawl management programming game. There's quite a bit to talk about this time, a bunch of small but impactful updates that move the game towards being more like an actual game, some small bits of art, and a peek at what building complex behaviors will feel like. Then at the end, I'll do another deep dive into the infrastructure and talk about the action system that connects the AI to the actual game systems. If you're new, this is a game about controlling a group of characters as they explore dungeons and bring back loot, which you use to upgrade the town, which makes the adventurers more effective, etc. Rather than focusing on high-level management of pre-designed AI characters, the core game is about programming the characters yourself using a graphical programming environment, or, for the truly adventurous, a low-level WebAssembly API. Players will be able to play the game solo, locally, or upload their AIs to a server for asynchronous multiplayer competitions. First off, there are some bits and bobs of art. I was sick of looking at the minimum effort trees I had, so I made slightly more than minimum effort trees. I modeled a little shrine to be the stand-in for the conversion station. A shrine with candles and a bowl for offerings is kind of a cheesy fantasy game staple, but it is absolutely what I had in my head while I was building the system, so I went with it for now. I think the long-term answer for this mechanic will be something more like feeding eerie monsters or doing business with Rossetti's goblin men, something like that. As a total aside, one of the things that is aesthetically in the back of my mind while working on this is Jake Wyatt's brilliant but sadly unfinished webcomic Necropolis, which opens with an explicit homage to the goblin market, which I love. I also set it up so that large objects like trees go translucent when the character the player is focused on moves behind them. I intend to have more complex scenery eventually, so this will only get more important. I'm using a dithering effect for this because, in the approximately half hour I spent fussing with it, I couldn't get Godot's renderer to handle translucent objects the way I needed. It's obviously possible, I just don't understand the rendering system well enough to make it work. Maybe someday. But the dithering effect was easy, and it actually looks pretty good, I think, so I might just keep it. Next, there's a whole pile of minor features and bug fixes, which culminates in the ability to set up more complex systems involving multiple characters of different classes, with different capabilities and behaviors, all interacting. I'm really thrilled to see different character classes working together. That's something I've known I wanted for a long time, and it's cool to finally have it in the game. There are currently two classes, referred to in the code very descriptively as Little Dude and Big Dude. The difference between them for now is their inventory capacity and their speed. Big dudes carry a lot more, but are very slow. One of the other changes is how pathfinding is handled. That has always been a service that the game provides to the AIs, but since the WebAssembly code is nearly as fast as native code, there's very little reason to keep pathfinding in the core game. The old pathfinding implementation had some problems too. Since it was centralized, it didn't have easy access to agent-specific knowledge like what areas they had explored, or types of creatures they might want to route around versus fight their way through. All that is fixable, but giving the AI direct control of its own pathfinding just makes it a non-issue. So now, a cleverly written AI can no longer use the fact that the buggy pathfinder exposes global information to map out the entire level in a single turn without ever even leaving the initial square. That would have been a pretty awesome exploit for someone to discover, but I'm sure there'll be others. Now I'm going to talk through the process of building a somewhat complex behavior in the visual editor. All of the nodes I'm using here are provisional while I'm testing out systems. The nodes in the final game will be at least a little different. We begin with the turn start node, which is an event that fires every time the AI needs to calculate an action. When it fires, it triggers whatever node it's connected to. In this case, the item is type node, which checks if the item under the character matches a particular type, fruit. It outputs a true or a false value and passes control onto the next node, a branch which checks the Boolean output and triggers one of two nodes based on its value. If the Boolean is true, then the character will try to pick up the fruit. If it can't for some reason, likely because its inventory is full, then it will continue on with the program. It checks what resources are present in its inventory. If there's at least one fruit, it triggers the Seen Items node, which lists all the items of type Shrine the character has seen. Then it tries to move towards the closest one. If there is no fruit in its inventory, then it will try to move towards the nearest fruit instead. When a character is standing near a shrine, they get access to its conversion action, which the character will attempt to use once it can no longer get any closer to the shrine. If the character has not seen any fruit or shrines, or it can't get to them for some reason, then it should move towards the nearest unexplored region of the map. Finally, I remember that it would be good for the character to hit any creature that comes near, mostly for the sake of controlling rats, so I stick that in at the beginning of the program. and with a bit of bug fixing to handle the case where the character's inventory doesn't contain any fruit, which I forgot about, the program works. And you can see the character walking back and forth between the fruit that the tree drops and the shrine, turning it into gold. Here you can see that program running alongside a second program that's using the larger character class to gather up the gold, and eventually, when its inventory was full, it will leave the level and deliver the gold to the town. Finally, let's talk about how the game communicates with the AIs. This is all about the low-level API rather than the visual coding system. Most of this stuff is not directly exposed in the visual environment, but is in the WebAssembly API. In previous videos, I've talked a little bit about the query functions that the AI can use to learn about the game. Things like getting a list of visible creatures or a list of items in the character's inventory. Those allow the AI to pull information from the game. The game can also push information to the AI about events which have happened to the character, like changing the location or receiving damage. Neither of those allow the AI to change the game state, though. So there's one final communication channel: actions. Each time an AI's entry point function is called, it's allowed to return a single action which determines what the character does that turn. In this game, there isn't a fixed set of actions. Instead, actions are defined by equipment, plus a few intrinsic ones, and the character can choose from the set of all actions supplied by the equipment they currently have. Actions can be generic, like attack with sword, or very specific to a special item, like push the third button on the golden widget of healing. Each action is actually a bundle of what I'm calling microactions, by analogy to microcode in the CPU. Microactions do come from a fixed set. Currently there are 8, but that will likely change. A simple action like swing sword might consist of a single attack microaction, which is configured with a range and damage. More complex actions, like the button on the golden widget, might be made up of several microactions, like one that immediately heals some health and another that applies a regeneration buff. All those microactions would take effect on the turn where the parent action was chosen, and would share its overall configuration, like a target, for example. A player programming the behavior for an AI might know what action a particular item supplies and reference it directly in their code, but more often the AI will need to examine the microactions within an action to understand what to do. For example, a character might have a bow and a sword, both of which supply some kind of attack action. When it comes time to attack a target, the AI will need to sort through all the actions it has access to and find the one with the attack microaction with sufficient range that does the most damage. But you need to be cautious because the attack action for a cursed sword might contain both a high damage microaction but also a negative buff, and if all you're checking is the damage of the attack microaction, your character could end up with a curse. Once the game receives an action from an AI, the rest is relatively straightforward. The action is broken apart into its component microactions, and those are individually handled by the responsible systems. This design makes it easy to compose together new complex actions, but more importantly, it allows AIs to be designed which can reason about completely novel actions. And, depending on how hard I lean into the roguelike aspects of the game, it could allow for procedural equipment with really interesting complex effects. Okay, that's it for this time, except for some channel news. There are now 100 of you subscribed, which is super awesome. I wouldn't have been surprised if the total audience for this weird niche project was exactly 0 people, but it's at least slightly more than 0, and that warms my heart. Thank you all for watching. Please join me again next time.